Year 13 Pure Maths revision video number 4. This video will cover 4 questions on the topics of differentiation, integration, trigonometry and parametric equations. Some topics may be interlinked as well within the questions. So we start off with a differentiation question, and it's very clear that this is a composite function. We have 3x squared plus 5 inside the brackets raised to the power 4. So this is set up for use of the chain rule, and we're going to differentiate this using the quick chain rule. This is a function of the format y equals f of x raised to a power, which means we simply need to multiply by the power, which is n, reduce the power by 1, n minus 1, but we then need to multiply by the derivative of this inner function, which means we multiply by f dash x. And we can do this with any of these sorts of power functions. So dy by dx is going to equal 4 bracket 3x squared plus 5 all to the power of 3. And we then multiply by the derivative of the inner function, which of course is 6x. This then gives us a final answer of 24x, 3x squared plus 5 all to the power of 3. So we move on to another question which involves an exponential function. The graph is of the function y equals 5x e to the minus 2x. We need to find the exact value of the area of the shaded region between the curve, the x-axis, and the line parallel to the y-axis through the maximum point on the curve. So in order to find this region, we need to find out this x value over here. Now, this x value occurs at the maximum point of the curve, so we're going to actually need to start by finding the coordinates of this maximum point, or finding the x-coordinate of this maximum point. So let's start with the function y equals 5x e to the minus 2x, and let's differentiate it. Now, this is a product, 5x and e to the minus 2x, so we're going to use the product rule to differentiate this. I'm going to say that u equals 5x, so du by dx is equal to 5, and I'm going to say that v is equal to e to the minus 2x, so dv by dx is equal to minus 2 e to the minus 2x. Remember, an exponential function differentiates to itself, so e to the minus 2x differentiates to e to the minus 2x, but we need to multiply by the derivative of this power here, so the inner function effectively, so multiply by the negative 2. So dy by dx is then equal to the following: u multiplied by dv by dx, so the product of this pair here, plus v multiplied by du by dx, which is the product of this pair over here. So let's fill those in. So u multiplied by dv by dx gives me negative 10x e to the power of negative 2x, and then I need to add on 5e to the negative 2x, v multiplied by du by dx. Now, let's call this maximum point here p, and what we know is that at p, dy by dx must equal 0, which tells me that minus 10x e to the minus 2x plus 5e to the minus 2x equals 0. Now, e to the negative 2x can never equal 0, which means we are perfectly okay to divide through all parts of this equation by e to the negative 2x. It cannot equal 0, so we can get rid of it. All 3 terms can be divided by it. So minus 10x plus 5 equals 0, so x is then equal to 1/2. So this point here has an x-coordinate of 1/2. So to then find the area, which is the last part of this, the shaded area, is going to equal the integral between 0 and 1/2 of 5x e to the minus 2x. And you then have to think of how are you going to do this integration, which technique is required, and of course this is going to require integration by parts. It's a clear product, and one part of the function does not differentiate to another part of the function, so integration by substitution isn't going to work here. So let's remind ourselves of how the integration by parts formula works. We want one part of this to be something we can differentiate and one part to be something we can integrate that doesn't become more complex. So u is going to equal 5x, so that du by dx equals 5, and dv by dx is going to equal e to the minus 2x, so v then equals minus a half e to the minus 2x. Remember, an exponential function integrates to itself. We then divide by the derivative of this power here. So the formula for integration by parts tells us we need uv minus the integral of v multiplied by du by dx, all integrated with respect to x. So let's start that off. So first of all, u multiplied by v, that's this pair here. So that equals minus 5 over 2 x e to the minus 2x. I'll deal with the limits in just a moment. And we want to subtract from that the integral of v multiplied by du by dx, which is the product of this pair here. So that's going to give us another minus, so this will become a plus overall, and then we've got 5 over 2, which can come outside the integral, e to the minus 2x dx. And again, I'm going to deal with the limits at the very end of this integral. So minus 5 over 2 x e to the minus 2x. Now integrating e to the minus 2x will give me e to the minus 2x, but I again need to divide by the derivative of this power, which is negative 2, so this becomes minus 5 over 4 e to the negative 2x, and of course I need to evaluate this between my limits as follows. So this is minus 5 over 2 multiplied by a half e to the negative 1, minus 5 over 4 e to the negative 1, minus, and of course e to the 0 is just 1. So in the second part, this term here becomes 0, but then this term here becomes, well, is minus 5 over 4. So let's tidy this up, and we end up with a final answer of 5 over 4 minus 5 over 2 e to the negative 1. So our next question involves trigonometry to start off with. We've got a shaded region which is bound by the curve y equals sine 3x and y equals 3 sine 3x. Obviously the curve with the higher amplitude is y equals 3 sine 3x, so that's the green function there, and then the lower function over here is of course y equals sine 3x. Now the question asks us to show that the area of this region is 4/3, which means this is also an integration question. Now, the area that's trapped between two curves can be calculated by doing f of x minus g of x, where f of x would be your higher function, g of x would be the one underneath, integrating those with respect to x and evaluating between a and b, where a and b are the points of intersection. Now, a is of course 0, this lower limit, but we need to know what this value over here is. So I'm going to call that point P. And what do we know? We know at point P, both sine 3x and 3 sine x equals 0. So if sine 3x is equal to 0, well, 3x could equal 0, but then that just gives us x equals 0, which is the origin. So that's not the answer we're looking for. The next time that 3x will equal 0 is when sine of pi equals 0. So 3x must equal pi, which then gives us x equals pi by 3. So at point P, x is equal to pi by 3. So our integral is going to be the area, the integral between 0 and pi by 3 of 3 sine 3x subtract sine 3x. And these are really easy integrals to carry out because we know that sine integrates to negative cosine. So 3 sine 3x will integrate to, first of all, let's think about the sine 3x. That will integrate to negative cos 3x, but we need to divide by the derivative of the inner function, and the inner function is of course 3x, and dividing by that 3 will cancel with the 3 here. So the result is just minus cos 3x. Now for the next part, over here, sine 3x will integrate to minus a third cos 3x. So this minus sign here will become a positive. So we'll get positive 1/3 cos 3x. And all of this has got to be evaluated between limits of pi by 3 and 0. So what does this then give us? This then gives us minus cos pi plus a third cos pi. Subtract. Now cos of 0 is just 1, so that gives me minus 1 plus 1/3, and then I'm going to tidy up this answer. So cos of pi is negative 1, so this gives me 1 minus a third plus 1 minus 1/3, which gives me a final answer of 4/3, which is good because we were required to show that the answer was actually equal to 4/3. So onwards to the parametric equation question. A curve has parametric equations defined by x equals 2 cot theta and y equals 2 sine squared theta for values of theta for which both x and y are defined. For what values of theta in the interval 0 to 2 pi is x undefined? So when do we get undefined values for x? So x equals 2 cot theta, which is the same as 2 over tan theta. So we're looking for angles which result in tan theta being 0, which causes x to be undefined. So if tan theta equals 0, well, tan theta equals 0 at 0, 0, pi, and 2 pi. So those are the values of theta for which x is undefined. So, part B. Show that the Cartesian equation of the curve is given by this result here, y equals a over x squared plus b, where a and b are positive integers to be determined. So we need to find the Cartesian equation for the curve. So let's take a look at our functions. X equals 2 cot theta and y equals 2 sine squared theta. Our aim is to eliminate theta from these two results. Now, if you are well versed in your trigonometric identities, you will know that based on the main identity, Pythagorean identity, sine squared theta plus cos squared theta is 1, there is a trigonometric identity that links cot and cosec. And cosec is 1 over sine, and that's the kind of reasoning that really helps answer a question like this. So from this identity, if you divide through by sine squared theta, you get 1 plus cot squared theta is equivalent to cosec squared theta. And that's the identity that we're going to use here. So let's start with that. 1 plus cot squared theta is equivalent to cosec squared theta. Now, we know that x is equal to 2 cot theta, so x squared equals 4 cot squared theta, which tells us that cot squared theta is x squared over 4. So we can rewrite this as 1 plus x squared over 4. Now, cosec squared theta, we know that y is equal to 2 sine squared theta. So we also then know that y over sine squared theta equals 2. Now, dividing by sine gives you the cosec function, so that's y cosec squared theta equals 2, or cosec squared theta equals 2 over y. So we can substitute that in for cosec squared theta here. Now we need to get this into the format y equals, so we need to do a little bit of rearrangement. So I've got 4 plus x squared over 4 equals 2 over y. And we're going to rearrange this, so I get y equals 8 over x squared plus 4. And it does say that a and b are positive integers to be determined, so we need to make it clear that we know the values of a and b. So a is clearly equal to 8 and b is clearly equal to 4. Now let's have a look at the last part of this question. We've got to determine whether or not Ali is correct. Well, the equation of the curve is y equals 8 over x squared plus 4. And for any value of x, x squared is always greater than or equal to 0, which means that x squared plus 4 is always greater than or equal to 4, so basically always positive, which means y is always positive, so yes, Ali is correct. Y will always be greater than 0. And y cannot be equal to 0. Try setting y equal to 0 and you'll end up with an equation that doesn't work.